z-tables. This is one simple z-table. Z-values are recorded and corresponding areas from the z-values to the mean of the standard normal distribution, which is always 0. In a vertical column, for example 1.03 is the z-value, the area is recorded in the cell next to the right. In universities, you still will see this table in which the z-value is divided in two pieces. For example, 1.14 is divided 1.1 plus 0.04. The first two digits, 1.1, are recorded in the vertical column, and then the third digit, or the value 0.04, is recorded in the horizontal, and the place in which the horizontal and vertical line crosses will give you the area that corresponds to the probability for z between negative infinity and this z value. It is 21st century, I believe, and we have online calculators. David Lane's online calculator is my favorite, and it shows not only the area immediately by just selecting area from z value and you put z value below, but it visualizes this z area. So this calculator, I will recommend you strongly to study this calculator. It's very interesting. It gives you 4 different areas, so select area from the z value and it will show you area above this z value, which is from the z value to positive infinity, below from negative infinity to this z value, between two z values, and outside two z values. But this calculator will do something else for you. Given the area, the calculator will tell you what are the two z values. For example, if area is 0.05, the z value will be 1645, below negative 1.645. The z value between two z values, we have area of 0.95 relative area, and the z values immediately will be calculated for seconds. And then let's go back to area 0.05. Outside the two z values that corresponds to the area of 0.05, outside of these two z values would be negative 196 and positive 196. How scientists and programmers record and calculate the area on the curve? Usually they use adjacent rectangles. The height of these rectangles, or the length of the rectangles, is f of z, and you know how to calculate f of z. I will show you if you don't. And then the area is f of z times the increment in which we divide horizontal axis. The area between two z values, z1 and z2, is the sum of all rectangles. If we need better resolution, we will use smaller increments. For example, in the first graph we have increment 0.5, in the second 0.1, which shows much better calculation of area under the curve. Visualizations, not enough for calculations, but for visualization it's okay. So every z value is the previous plus 0.1, and then I will copy this formula. My z-axis is ready. Next, I need to make the f function, which is this formula here, 1 divided by sqrt of 2 times pi. And my pi is recorded in this cell here. I need this pi to be constant, not to change, as I copy the formula, times exponent of negative 0.5 times the cell in which z value is recorded, squared. And I will copy this formula once again. That way I have z and f of z. quite enough for visualization, but I will need a beautiful visualization. I will copy z and f of z values as values, not with the formula, and I will try to achieve this graph. So this is what I did. I copy z value, then I copy z value again, left only the whole values so that I have beautiful horizontal axis, beautiful information about horizontal axis. F of z I have twice, once all f of z and then f of z only in the interval in which I want to visualize the probabilities under the normal curve. So from negative 2.1 to 1.2, only this f of z I copy. This is the block that I want to show as probability or area under the curve, which is the same. Then I will get these three columns. The first is horizontal axis and the other two vertical values. Insert column, and that's it. Let's make it a little bit bigger. I will clean all this. Then I will select only the column with f of z. Change type, it's the upper left corner, and we'll select second line, which is stacked line. Okay. Then right click, format data. I need to not to have gaps, and the visualization is ready. Next step is to calculate something, to calculate the probability. For calculation I will need much better increment. For example, I will use for the z value increment of 0.0005. I will copy this formula. So pay attention that I am calculating something that only David Lane or only the applets are giving so far. I calculate from negative to positive values, and they are two different values. Then I have the f of z, which is sqrt 2 times pi, and pi needs to be constant, so $sign, times exponent of negative 0.5 times this cell D4. You cannot see it because the formula is going there squared, and I will copy this formula from z negative 1.3 to z positive 1.35. Next I need my rectangles, and the rectangles are this value times the increment, which is 0.0005, length times width. Okay, and I will copy these rectangles as well in the area of interest. Finally, I need the cumulative probabilities, which means that I will copy this first rectangle, but I will put the rectangle as a number. And I have here interesting formula: the previous rectangle plus the current rectangle on the right side. This is cumulative, this is these two together. And then I will copy the formula for cumulative probabilities. And the last cell, 1.35, I need to show it, is recorded in D963. It should be a cell above because we have right rectangle, so it should go exactly to 1.35 but not after 1.35. So this right rectangle you have to visualize in your mind. So this is equal G4963, and this is my probability. Now I need to show you how what is the probability of David Lane's calculator between negative 1.13 and positive 1.35. He has this 0.13 7823, which is a very good compared to very well done calculations. Now in the future, if you want to create the entire z-table, you have to start here at -4 probably to +4, and you will have all cumulative probabilities as they were in this university type of table, and you will be able, from given the area, let's say, to find the z-value.